This clock is actually slow. I just found out, so I think we're a little late. But I think, yeah, we do have a few folks online, so maybe we'll get started. Good morning, everybody. Welcome to the second day. Okay. Welcome to the second day of the mathematical modeling of tumor immune dynamics and immunotherapies workshop. We had some really fantastic discussions yesterday, so today we'll continue in the same spirit. I don't know if we have any logistical items, Morgan. Yeah, okay. So, okay, since we don't have any other updates, I'm just going to get started by introducing the first speaker for today. So it is my pleasure to introduce Dr. Maxim Kuznetsov, who is currently a postdoc at the Russ Ruckney lab at the City of Hope. And we decided we don't know since when, but we think 2023. Prior to that, he received a PhD in Russia in mathematics and physics. So this was a transition. So now he works in mathematical oncology, does really fabulous work in the space of fractionation of radiotherapy dosing and solid tumors. Optimization of targeted radionuclide therapies for blood cancers. I think we'll hear a little bit more about that, and lots of really interesting work. So today, I think we're going to hear a little bit more about optimization of doses and regimens, which was a discussion that we started yesterday. I think there's going to be more multiple myeloma, right, Maxim? Okay, yeah, great. So if you don't like multiple myeloma, well, I guess now you might learn to like it. So yeah, today we're going to hear about optimization of radioimmunotherapy of blood cancers, insights from mathematical modeling. Thank you, Maxim. And by the way, we do have folks online, so if you have a question, please raise your hand and then we'll come around.
Yeah, hello. Can you hear me?
We can hear you.
Yes, and it seems that the mic is working. So thank you very much, Berta, for a wonderful introduction. It's hard to like a disease, but yeah, I like the mathematical problems. And one small correction, which is not obvious from my CV, my transition began earlier because my PhD is already at the major of biophysics. So I have a little bit more experience. So thank you for the opportunity to present the results of my work here today, which was performed in collaboration with these wonderful people. This work covers a quite specific type of immunotherapy, which is radioimmunotherapy, and I'm gonna cover specifically blood setting. This study is based on our mouse experiments on disseminated multiple myeloma, which is a white blood cell cancer resulting in about 100,000 of deaths worldwide annually. Its cells overexpress CD38 receptors, which can be targeted by daratumumab. The main mode of action of daratumumab is induction of cancer cell killing by immune system. It has a very favorable safety profile, but tumor relapse represents a very frequent and seemingly inevitable issue. And relevant studies suggest that the mechanism of multiple myeloma resistance to daratumumab is associated with immune escape, while the relapsing patients generally have stable expression of unmutated CD38, which preserves their ability to be targeted by daratumumab. In light of this, it is encouraging to guide delivery of radionuclides, that is, chemical elements that release radiation, to multiple myeloma cells. Two main types of radionuclides are investigated in trials. One of them is beta particles, which is just a historic name for high-speed electrons. They deposit comparably low energy over long distances. And the second type of radionuclides is alpha particles, which are two protons and two neutrons bound together. They deposit higher energy over shorter ranges corresponding to just one or few cell diameters. Previously, our group has compared the efficacy and toxicity of two radionuclides conjugated to daratumumab in a mouse model, and we concluded that the use of actinium-225 is more prominent for clinical translation than lutetium-177, which is a beta particle emitter, while actinium-225 is alpha particle emitter. And now we are conducting a phase 1 clinical trial for assessing its safety for patients. Actinium-225 has a half-life of about 10 days and emits 4 energetic alpha particles within 1 or few hours. Radiolabeling of daratumumab notably increases its efficacy, but however, some questions remain open. One of them is how to administer radioconjugates the most optimal way. Radionuclides spontaneously emit particles in random directions, and only some of them affect cancer cells. And radionuclides circulated in blood pose a significant threat to well-perfused, rapidly proliferating organs like bone marrow. Therefore, radionuclides suppress hematopoiesis, and red marrow is always considered as a crucial organ at risk for radioimmunotherapy. It isn't clear whether we can achieve cure, at least in mouse model yet. Formally, cure implies elimination of every single cholinergic malignant cell, while even a residual, technically undetectable number of them can promote tumor recurrence. And treatment efficacy can be compromised not only by dose-limiting side effects, but also by the inherent restrictions of cancer cells exposed to drug. The choice of proper therapy protocol is further complicated by intermouse variability. We claim that mathematical modeling can help navigate this complexity and facilitate optimization of radiotherapy. Eventually, it may help optimize radiotherapy in clinical settings, since the obtained principle can be translated in clinics. Here's our data on cancer growth in mouse model of disseminated multiple myeloma. We used fluorescent cancer cells that allows monitoring the cancer burden via imaging. The data includes a control group, 5 colorful groups treated by radiolabeled daratumumab, where the unit of nanocurie implies 37 radioactive decays per second. Also, there was one group treated with radiolabeled trastuzumab, which is another antibody not binding to multiple myeloma cells. Therefore, in this setting, they were affected only by decays of nucleids unattached to them and freely floating in the bloodstream. The injected drug also contained unlabeled daratumumab and in large quantities. That was due to 2 reasons. Yes, question?
Maxim, I have a question about these mouse models. What kind of models are these? Are these like xenograft models?
Yes, these are human xenografts.
And so how does that compare, right? Because we know in humans, multiple myeloma has lots of complexities, bone marrows, but, there is also extramedullary disease and other. So how relevant, do you think that that model is compared to the clinical sort of presentation of this?
That's a great question. Of course, it
Mhm.
has a lot of limitations, like any models do. And as a mouse model, it has more limitations if you would try to straightforwardly translate it in clinical setting.
Okay.
The thing is that I don't try to do it yet.
Okay.
Now I'm talking just about mouse model, and my goal right now that I would like to achieve is to prove that radioimmunotherapy can be optimized in mouse setting. After I show that, I'm going to translate it to clinics.
Oh, okay. All right, great. Thank you.
Yeah, but I will cover some of these aspects further. And well, I will not cover extramedullary disease, but we have experiments on them, which are quite fascinating. So if someone wants to hear about it, ask me. So, injected drug contained unlabeled daratumumab and in large quantities, and there was 2 reasons for that. Firstly, for our experiments, radioconjugates were prepared by incubation of daratumumab with actinium at a specific labeling ratio, which yields about 1800 of unlabeled antibodies per 1 radioconjugate. And I will refer to this parameter as drug impurity. The crucial problem that prevents the use of higher labeling ratios is the accompanying decrease of radiolabeling efficiency, which is defined as the percentage of the initial radioactivity used that becomes successfully incorporated. And this labeling ratio was chosen since it yields close to 100% of radiolabeling efficiency. Therefore, all the used daratumumab literally was incorporated, which was considered as a good thing because actinium-225 is expensive and nowadays also challenging to obtain. And secondly, experimentalists further diluted each dose in unlabeled antibodies in order to use the same total amount of daratumumab for each dose. And this resulted in these coefficients of drug impurity, which depends on the dose. Dealing with this mouse model allows to introduce 2 simplifications. Firstly, we can neglect the own action of daratumumab since we used immunodeficient mice, and it did not affect the cancer growth in them. Secondly, we can neglect binding of antibodies to normal cells for now, since we use human cancer xenografts and human antibodies. And here's the scheme of the mathematical model, which reflects the considered processes. It contains 9 variables, and I will present the equations governing their dynamics step by step, so you will see a lot of equations today. I will refer to antibodies that are linked to yet undecayed nucleids as active antibodies. So injected dose contains active antibodies and inert antibodies. And the injection terms result in their instantaneous increase of their concentration in blood and represent their external control of the otherwise autonomous system of equations. Upon exponential decay, antibodies become inert, and antibodies can bind to free receptors on cancer cells or be cleared out. Viable cancer cells proliferate continuously unless they are damaged by radiation. The term of radiation damage depends on several factors, and I will return to it shortly. Damaged cancer cells stop proliferating and gradually die, releasing into the bloodstream the fragments of antibodies, some of which still contain radioactive nucleids. These fragments cannot bind to cancer cells. Question?
Can I just ask about the proliferation term? So you're including just exponential growth. Is that like a consequence of your mouse model? Or is it in some way?
Yes, absolutely, because it grows like this, like at least due to up to that tumor burden. Yeah, this is logarithmic scale, and this is
okay. So
like
you never
nice
see in your models any plateau. It's just
in subcutaneous setting we do.
Okay.
In blood cancer setting, well, it seems that it really grows exponentially until it kills the mice.
Okay, gotcha. Thanks.
So both active antibodies unanchored to cancer cells and their fragments can decay in blood affecting red marrow or be cleared out. And the clearance rate of fragments is higher than that of intact antibodies. And I explicitly monitor the state of specific receptors on both viable and damaged cancer cells. Receptors can be free, bound to active antibodies, and bound to inert antibodies, with the fractions of each state being the numbers from 1 to 0. Since the sum of fractions of 3 states on the same type of cell is always equal to 1, we can monitor only 2 states. These equations are obtained pretty straightforwardly, given that viable cells produce free receptors during proliferation. The binding of drug and nuclear decay affects the state of receptors, and the damage of cells changes the type of cells that the receptors are residing on. For treatment toxicity, we consider only the decays of radionuclides unattached to cancer cells for now. In other words, we assume that the particles emitted from nuclides anchored to cancer cells effectively deposit all the radiation in them. Therefore, the nuclides decays are mainly toxic when the antibody is unbound, curative when it is bound, and toxic again when its fragments return to blood. Antibody receptor binding is considered to be irreversible. This is a simplification based on the fact that daratumumab is rapidly internalized in multiple myeloma cells. And for simplicity, we don't consider internalized antibodies as a separate variable. We just assume that they stay bound. Yes?
Can I ask another question? This is really interesting. Sorry about all the questions. But so for the cells that are damaged, is there still binding that happens? Like, do they have receptors?
Yes,
in this
if there are free receptors, they can bind to cancer cells.
They have free. So what?
If
what
they
does,
have it.
Okay, so what does that mean? How do you define that? So a damaged cell is still intact in your model and has receptors, like what?
For some time, it dies gradually.
Okay, so do you have multiple death states? Because that's also
no, I
that
don't. Now
do.
it is approximated with like a simple exponential death term. So yeah, the model is rather rough. The thing is, it's not quantitative at this stage. It is qualitative.
But okay, so your damaged cells though can still pretty much bind to drug, right? So until they disappear.
Until they disappear. Yes. Well, that is based on the clinical findings. At least, yeah, books by clinical biology claim that a large fraction of cells dies only at mitosis after being damaged by radiation. So for some time they are still alive but not viable.
Okay. So they already have, but they don't produce receptors, like that. You don't have production.
I assume that they don't do it.
Okay.
Yes. Once again, the model is rough and qualitative.
Okay.
Maybe, yeah, in reality, it takes some time, you know, but.
Okay. Okay. Yep. Thanks. More question.
So again, just to complement this question, so these damaged cells, they they after that they go to apoptosis, or they just like break up, or how, like because you said that some of the these is like released, like the antibody.
Yeah, just due to the sheer conservation of mass. So like the nucleids cannot disappear; they have to go somewhere.
Oh, okay.
They are already in blood, like it's a blood cancer.
Thank you. I would also like to follow up on this, and it's more of a biology question. Should we think about these damaged cells as like connected to senescence or something?
Oh, that's a very, very deep question, because yeah, after radiation damage, cells can behave differently, and they can undergo apoptosis, necrosis. They can go to senescence and remain alive, but not clonogenic, which is like also contributes to cancer cure because they will not proliferate. And
so in
like,
your case, it's more like introducing a delay between when you get the damage
yes,
and when you actually
yes.
die.
So
Okay.
in order to not have 1,000 equations for now, just like for the sake of qualitative reasoning,
No, yeah,
I
yeah,
just
yeah.
assume that they gradually die. Yeah, but if you want to fit it to a specific data, you will have to like study it all.
No. It's like it was just to get an idea of the biology.
Yeah,
I'm not arguing with the model.
Sorry, I guess my question is also along the same line. So I understand you're building the model and it's qualitative, but could you say so you showed some data earlier. Could you say a little bit what aspect of that data you want to capture, or what is it about that you want to qualitatively explain through the model?
Well, that's basically my whole presentation is about it. So
Okay.
can I answer like in 40 minutes?
All right. All right. So nothing in the first plot you can tell us that's useful for us right now. No. Okay.
Well, I assume that the model should be understood, so that's useful. Yeah, so the binding is irreversible. We assume that the drug just stays bound. Importantly, concentrations of antibodies in blood and cancer cells microenvironment are assumed to be equal, since multiple myeloma cells are predominantly confined to the bone marrow sites, which are subject to very rapid exchange of substances with the bloodstream. The most interesting mathematical function in this model is the function of radiation damage. It has 3 terms multiplied by a single parameter of cell radiosensitivity, which is reasonable for modeling the effect of high energetic alpha particles. The terms of self-damage and crossfire stand for the damage of a cell due to the decays on its own receptors and on the receptors of neighboring cells. The numerators in these terms denote the rate of decays within a certain volume provided in denominators. The range of alpha particles in tissue is greater than a cell diameter, but not much. Therefore, both these processes should be significant, while the coefficient of significance can be varied from 0 to 1, which turns out to be quite useful. And the third term accounts for the damage of cells due to the decay of unanchored nucleids. As our experimental data with radiolabeled trastuzumab shows, this part plays only a weak role in the overall damage of cancer cells. But since the term stays for decays in blood, it is also proportional to the amount of toxic decays by our assumptions. And I will organize the modeling results as follows. At first, I will consider idealized single-dose treatment by pure radioconjugates, which means that all the injected antibodies are conjugated with radionuclides. Understanding this case serves as an important stepping stone for further results related to the effect of drug impurity on single-dose treatment and to multi-dose treatment. So, one injection of pure radioconjugates. If the amount is notably lower than the amount of specific receptors on cancer cells, then their binding is performed only within several hours, while the concentration of antibodies in blood falls rapidly. And this greatly facilitates analytical investigation of model in this setting. This is an example of cancer cell dynamics under prolonged irradiation, when the number of viable cells goes down and treatment begins, and the minimal number is achieved when the rate of nuclear decays falls to the level at which they are not able to compensate for the ongoing cancer cells proliferation. The ratio of minimal number of viable cells and the initial number can be regarded as the minimal surviving fraction. And this parameter can be estimated analytically for the cases where only self-damage or only crossfire contribute to the treatment efficacy, if the treatment works, in the sense that the minimal number of viable cells is much lower than the initial number. Due to the fast antibody binding, we can use the approximation that at the initial moment, all the drug occupies the cancer cell receptors, resulting in this fraction of active receptors. Then in self-damage only case, for the estimation of minimal number of viable cells, only two equations matter. Viable cells proliferate and get damaged by radiation, which rate depends only on the fraction of active receptors on viable cells themselves, since only self-damage matters. This fraction exponentially decreases, and it is easy to solve this independent equation, and the explicit solution for the number of cells can also be obtained, no big deal. In crossfire only case, the situation is a bit trickier. Here, the active receptors on damaged cells also matter. But we can note that during the first hours of treatment, when damaged cells just begin to emerge, the fractions of active receptors on viable and damaged cells are close to each other and can be approximated as one variable, while if treatment works, then already after a day, the number of viable cells is very small compared to the number of damaged cells, and we can approximate the rate of radiation using only the active receptors on damaged cells. The number of dead cells, however, also matters, but we can make further approximation using the assumption that during the initial period, the total number of cells does not change drastically, and just replace this sum of cells with their initial number. Then we obtain this system where both viable cells and active cells depend on quadratic terms, which include their product, just like in the famous Lotka-Volterra system, but with different signs. And this system cannot be solved analytically, like in Tyler's case, but an interesting feature of it is that it has a certain conserved quantity. Like the Lotka-Volterra system has a conserved quantity, which stems from the fact that its solutions are periodic. And this system also has one, although its solutions are not periodic. So the number of viable cells initially decreases and then regrows, and the number of active receptors and the fraction of them falls down monotonically. But yeah, we can obtain this function, differentiate it, and find the location of its minimum and the minimal number of viable cells. And we can find these formulas for the minimal surviving fraction of cancer cells. Okay, but yeah, what's the point of doing this, you may ask, and why should clinicians care? Well, the nice consequence is that these equations effectively depend only on two combined parameters. The first of them is the ratio of cell proliferation rate and nuclear decay rate. When it tends to 0, both formulas tend to this expression containing the second combined parameter. And this expression corresponds to the instantaneous decays of nucleus. And not surprisingly, it also coincides with the classical formula for surviving fraction of cells after instantaneous irradiation, widely used in external beam setting. As you can see, the comparison with numerical simulations shows that these formulas give small errors unless the nuclear decay rate is very fast. In this case, a large fraction of nucleus simply decays in the bloodstream before anchoring to cancer cells. So, with the increase of cancer cell proliferation, the minimal surviving fraction grows, but faster decay of nucleus can mitigate it. And from this perspective, the use of radium-224, which decay chain yields about 2.5 times faster release of similar alpha particle energy, represents a potentially more effective option for treatment of blood cancers. And this is the first qualitative conclusion of modeling. Notably, self-damage case is less effective than crossfire only case, and this happens because the density of radioactivity on viable cells decreases not only due to the decay of nucleus, but also due to redistribution of nucleus among the newborn cells. As the cell volume increases, the density of nucleus falls down, and the density of energy radiation also decreases. Therefore, after binding of antibodies, the fraction of active receptors on viable cells decreases faster than that on damaged cells. Given the continuous nature of our modeling approach, the numbers of cells are expressed as real numbers, which can be much less than 1, say 1/2 of a cell or 1/100th of a cell. But what does it mean? Is it cure or not? The classical approach towards interpretation of tumor cure probability is as follows. Imagine that the minimal viable cell number is 1/2. Then what you do, you take 100 of identical baskets, which represent tumors, and you take twice less cells, which is 50 cells. and you randomly assign them to these tumors. As a result, some tumors will contain 1 cell, some will contain 2 cells, or even 3 or more, but there will be a fraction of empty or cured tumors. As follows from Poisson distribution in the limit of infinite number of tumors, the fraction of cured ones can be estimated by this formula. So half a cell means 61% of tumor cure probability. And I hope this answers the question that was asked in the chat yesterday. For convenience, I will take 99% of cure probability as definite cure. So if number of viable cells falls below 100th, then cancer is cured. Otherwise, it is not. And why is it convenient? This allows introducing the minimal single curative dose as the dose resulting in this minimal number of viable cells. This plot illustrates the influence of relative significance of self-damage versus crossfire on the minimal single curative dose, once again emphasizing the qualitative difference of extreme opposite cases. For self-damage, we need greater dose to achieve cure. And there exists a nice way to get analytical estimations of curative dose for the arbitrary value of the significance of self-damage Ks. We already know the formula for the crossfire-only case, and if we neglect self-damage, then the function will behave like this. So it will be equivalent to the situation where the cell radiosensitivity falls down along with the increase of Ks. And eventually, curative dose will go to infinity as Ks equals to 1, since at this point we have no crossfire, and also by current assumption, no self-damage, and we need infinite dose to cure cancer. But we do have self-damage, and we do know the estimation at this point. So if we take this graph and just stretch it so it clicks here, then we get a nice approximation of minimal single curative dose. And I have no idea how this reasoning can be useful in clinics. It's just mathematically satisfying, and this is a mathematical conference. But importantly,
Max,
yes?
I can ask a quick question, and maybe you'll answer it already, but I'm really curious. So you were talking about the number of tumor cells, but really the game here is about receptors, right? So how do you have like a explicit receptor counts for each cell, or how are you making that connection between numbers of cells and then receptor numbers?
Yeah,
Do you see what I mean?
I do explicit receptor counting.
So how do you convert that into numbers of cells?
Well, once again, in this qualitative model, I do it pretty straightforwardly. The cancer is homogeneous. Each cell has.
So you're assuming
some
like
number.
a fixed density of receptors per cell, and then that's how you convert.
Yes. I also played around with heterogeneous model, and I refer the interested readers to the supplementary of my paper that has just now been accepted.
Okay, but yeah, so you're counting receptors in your model equations, and then you're converting to tumor cells by assuming a fixed density, or how are you?
I don't do it straightforwardly. I would put it this way: the game is to minimize the number of viable tumor cells using the attachment of radionuclides to receptors.
So your binding rates are receptor dependent.
Well, like effective binding rates, like binding rates of the whole tumor, are effective dependent. Size dependent. So depending on the size of tumor.
But there's, I guess, what I'm trying to ask is, you're not explicitly counting how many receptors you have in total at the tumor level.
I do.
You do.
I do.
Okay.
Well, it's easy.
Maybe
Just
we can take that
multiply.
offline. We can talk a little bit more. We can talk a little bit. I don't.
Yeah, that will be explicit further. So.
Okay. Great. Thank you.
Another question?
Sorry, I also missed something in the model. So in your model, the tumor cells go down and then come up, while the receptors are going down. That's what you said. Maybe I misunderstood.
No.
Okay, so
no.
Could you explain the non-monotonicity and what was that was not time axis, but probably some other axis, right?
Yes. So the thing is,
the dosage or?
Yeah, let me clarify. In numerical simulations, the number of cells, the viable cells, always goes down and always goes up, because even if you have 10 to the power of minus 100 cells, well, these are numerical simulations, it will keep exponentially growing.
Because you only give one dose. So that kills whoever it kills, whatever is left then grows back.
No, no matter how many doses you give, in numerical simulations, in idealized one, if you
you're
can,
not assuming extinction. Okay.
If
there's no extinction. Okay.
So like if you can express the number like in using as many bytes, as you
So
want,
if you
it
stop,
will
right, if
exponentially
you
increase
stop
that.
somewhere, it's going to grow back.
So the reason is how to define cure. And this graph, was related to this system. This is viable cancer cell number depending on the fraction of active receptors. So the number of receptors does not necessarily decrease. It's the number of active receptors that decreases. And active receptors are the ones that contain radioactive nucleids, and they decay. They stop being active.
It's a bistable system. You're saying at some active receptor level, you can have high or, sorry, so how do you read this graph? So
this system does not have an attractor point if you perform just a single injection.
I see.
Because like the
It's
cancer is
just
going to
dynamic,
grow,
right.
so the attractor point is infinity.
Wait, sorry, you gotta
That's a phase path. That's a phase path in a phase parameter. So yeah, that's why I talked about like low covalent system. Yeah, its phase path is like oscillating. This one is not, but it's still useful.
Maxim, my question is about the previous slide,
You mean the following one?
or the following. Yeah. No, the one with two formulas on the bottom. Go forward, please. One more, I think.
No, this is the filter I used.
Yeah, this one.
Okay, yeah.
So for these two formulas on the bottom of the slide, it looks like you are dealing with conditional probabilities, but these are not the probabilities.
These are not the probabilities.
Because like you have two conditions.
Well, you know, the number of mathematical functions is limited. So like some formulas resemble other formulas, especially when they have exponents in them.
These are like for averages, basically. Yeah?
This is this model is not stochastic. This model is deterministic. So like this is the
So it's a good answer.
definitive ratio of the minimal number of cells and the initial number. That's it. Under like two conditions, this is like variation of parameter. And for these settings, there is an analytical summation. Great. I expected the total time of questions to be 15 minutes. So now I begin to worry. No, that's great. That means that it's interesting. So yeah, the curative dose, importantly, and this might be important for clinics, it can be converted into the number of radioconjugates initially residing on each cancerous cell that eventually will lead to cure. And for this variation, it spans from about 76 to 270, which is much smaller than the average number of CD38 receptors on multiple myeloma cells that we use in experiments. For patient data, a range of median numbers of CD38 per multiple myeloma cell spans more than an order of magnitude, with the minimal number being about 16,000. And that is still a lot. If we attach 16,000 guns, which however are shooting in random directions, to each cancer cell, then we have a pretty good chance of eliminating each of the billions of cells. So there should be no problem in curing multiple myeloma, right? Wrong. Because in practice, the binding of radioconjugates to cells is accompanied by binding of inert antibodies to them, which are not only the impurities of the drug, but also the previously injected antibodies remaining in the bloodstream, which nucleids have decayed. And this significantly reduces the number of guns that can anchor to cancer cell. And if we shoot only several bullets at a cancer cell, then we have a notable risk of missing all the shots, keeping some of the cancer cells alive. And in this case, the cancer will strike back. And this highlights the importance of nucleid to antibody ratio for treatment efficacy. And let me emphasize that for these results, we neglect the unbinding of drug, which we believe is a valid assumption since the daratumumab is internalized by multiple myeloma cells literally within an hour or several hours. And what if the drug would not internalize and would unbind from cells? This plot shows what would happen. As we decrease antibody affinity, the range of particles becomes less significant since the redistribution of radioconjugates from damaged to viable cells mitigates the decrease of nuclear density on them due to cells proliferation. So this graph suggests that the use of short-range particle emitters and high-affinity antibodies is not a good option for a single dose using significantly pure drug. But when we use impure radioconjugates and multiple doses, the situation becomes different. let's gradually increase the coefficient of drug impurity, diluting the radioconjugates in unlabeled antibodies. As we do it, there is a certain threshold after which the minimal single curative dose increases drastically, and this threshold is defined by the number of antibodies that cancer cells can anchor. If we neglect the damage from unanchored nucleids, which float in blood, then it just skyrockets, implying that cure is impossible. Since there is some small efficacy, the cure is possible, but only if we inject dramatic doses associated with strong toxicity, which rapidly becomes lethal. And for mathematical convenience, I will refer to all the doses that allow decrease in viable cell number to the curative threshold, 100, as curative, implying that they can be curative but lethally toxic simultaneously. And now let's zoom into the initial part of this graph. For crossfire-only case, the curative dose remains almost constant while it fits all the receptors present at the cancer cells at the moment of injection, and even a bit beyond, because cancer cells proliferate to some extent before they are all dead, thus increasing the cancer capacity for drug binding. And self-damage only case shows different behavior. When the amount of antibodies approaches the amount of receptors, the curative dose starts decreasing. This happens since the new free receptors are produced only by still viable cells in the model assumptions. Therefore, when cancer cells are nearly saturated, yet a substantial amount of radioconjugates remains in the bloodstream, then viable cells attract radioconjugates at a faster rate than damaged cells. In the case of significant self-damage, the radiation is therefore redistributed towards viable cells, contributing to the increase of treatment efficacy and to the decrease of curative dose. This plot highlights the idea showing the fraction of injected dose delivered to still viable cancer cells in the same simulations. So in case when self-damage is prominent, moderate oversaturation of cancer binding capacity allows increasing this parameter. But note that it is rather low. It's less than 3% here, and under broad variation of model parameters, in reasonable limits, it does not go much above that. And the majority of radiation is deposited in already damaged cells, and thus formally does not contribute to treatment efficacy. And it is not difficult to estimate the upper bound of the fraction of injected radioactivity that is spent on viable cells for a single dose setting. Let's consider another idealized situation where cells don't proliferate and don't die, but do get damaged. In this case, the minimal fraction of surviving cells can be expressed this way, where D is the total radiation energy per cancer mass. And let's imagine that we increase it gradually, starting from 0 up to the value leading to cancer cure. As we do it, the viable fraction of cells decreases, and increasingly greater fraction of radiation is spent on already damaged cells. Yeah, to obtain the total fraction of activity spent on viable cells, we need to find the integral, and here's the answer. And this is the upper limit for the fraction of activity spent on viable cells, since when cells proliferate and die, it can only decrease, as confirmed by modeling. And this result is really nice, since it depends only on the minimal surviving fraction of cells and is independent of other parameters. So, for example, if you want to decrease cancer cell number from, say, 1 billion to just 1, then by a single dose, then you will use only less than 5% of radioactivity on still viable cells, and you cannot overcome this threshold no matter what. And the key to the increase of treatment efficacy is redistribution of irradiation towards still viable cells. However, this redistribution by itself does not guarantee the decrease of treatment toxicity, because when cancer cells are closer to saturation, their remaining antibodies bind slower and stay in blood for a longer period, amplifying the toxic effects and answering the Blurter's question. In case of significant self-damage, you still can decrease the overall treatment toxicity, but in intermediate case, this may not happen. And this gray line marks the labeling ratio that our current experimental technique yields. So it's 1 radioconjugate per about 1800 of unlabeled molecules, and I will use this parameter for all the further results. So one of the main conclusions is that cancer binding capacity plays a decisive role, which is the total number of specific receptors on cancer cells. It plays a decisive role on whether cancer can be cured by radionuclides without exceeding lethal toxicity. And it is confirmed by a global parameter sweep. this is the scatter plot of minimal single curative dose and cancer binding capacity, which is the product of the number of specific receptors per cancer cell and the initial number of cancer cells. For this line, the amount of injected antibodies is equal to it, and all dots below correspond to low toxic cases. Ongoing cell proliferation also renders these cases low toxic, as modeling shows the number of newborn cancer cells in this model is unlikely to exceed half of the initial number when you apply minimal single curative dose. And it justifies the low toxicity of the cases where the amount of injected antibodies is lower than 1.5 of cancer binding capacity, plus a small parameter that compensates for slow binding under small amount of specific receptors. And this provides an idea for a personalized dosing strategy based on only one parameter, cancer binding capacity. In the idealized world described by this model, it can be estimated before treatment. As I've showed, the concentration of drug in blood initially after its injection follows exponential decrease, which rate depends on the binding rate, the volume of drug distribution, and on the cancer binding capacity. Therefore, a preliminary injection of diagnostic radioconjugates, which would occupy by themselves a negligible fraction of receptors, can shed light on the cancer binding capacity in this highly idealized reasoning, while in reality everything is not so simple. But please, let's just assume for now that cancer binding capacity can be estimated before treatment. And I will discuss reality towards the end of my talk. Yeah, moreover, to ensure that the dose will not be significantly toxic, it is in theory possible to estimate maximal safe dose using the physiological ranges of other parameters, so that the injected dose will not result in lethal toxicity, no matter which parameters the mouse have. These personalized single-dose settings were tested for another set of virtual mice, which can die either due to toxicity when the number of toxic decays reaches lethal level, or due to cancer burden. And these curves correspond to treatments by personalized cancer binding capacity-based doses, where the number of injected radio antibodies is about 1.5 of binding capacity. And these are the curves corresponding to maximal safe single doses, which for this study bring only a minor alteration in efficacy at the expense of increase of toxic decays. These curves show the results of personalized numerical optimization, assuming precise knowledge of all parameters for each mouse, with the goal of curing a mouse if it is feasible, otherwise prolonging its survival as much as possible. So the curative rate of approaches based on cancer binding capacity is only slightly smaller than this theoretical limit, and their outcomes are achieved without approaching the lethal level of toxic decays. And this is really important. The treatment becomes less toxic if we just don't oversaturate the receptors on cancer cells. And this indicates that personalized dosing strategy based on cancer binding capacity has a great potential in single dose setting at least. How much do we gain from it? Here is the administration of maximal one-size-fits-all dose, not leading to toxicity-related deaths. Well, it's also quite efficient, but it is notably more toxic than the cancer binding capacity-based treatment. Moreover, the personalized approach can be projected onto multi-dose setting, and that's where things become the most interesting. So let's proceed to multi-dose treatment, and at first, let's also find the theoretical limit for multi-dose optimization, assuming the precise knowledge of all model parameters. But if we use multiple doses, then we face the problem which generally accompanies the multi-dimensional optimization tasks. It is easy to find a local optimum, but it is hard to find a global optimum, and it is often impossible to prove that the found optimal is global. So let's initially consider two-dose treatments, and in case of two doses, the global optimum can be found. Let's represent our curative two-dose schedules on a phase space, where the first parameter is the ratio of the first dose in this two-dose schedule and the minimal single curative dose, and the second parameter is the interval between doses. And these two parameters identify a two-dose schedule unambiguously because its second dose represents a uniquely defined minimal dose leading to cancer cure when injected at specific moment of time under that conditions. And here's the example of the work of the algorithm of two-dose optimization. It involves a series of steps which are performed if they lead to the decrease of the amount of toxic decays indicated here. And here are the model simulations with the two-dose optimal schedules for crossfire-only case. As I told earlier, the key to the increase of treatment efficacy is the redistribution of irradiation towards still viable cells. And how can it be achieved in the situation when each of the emitted particles traverses a long distance and damages a lot of cells, or this goes through a lot of cells? Well, we can induce the initial cancer shrinkage by a moderate dose that will leave a notable fraction of receptors free, as shown here, for viable and damaged cancer cells. Then we can wait until a significant number of damaged cells die and inject the second dose. It will be distributed over a smaller number of cells, and therefore we will need a smaller dose to reach cure. So in this example, the optimal two-dose schedule yields about 6% fewer toxic decays in the bloodstream. So the decrease of cancer cell number during treatment is the main factor that enables treatment optimization when crossfire dominates. When self-damage dominates, the decrease in toxicity can be much more prominent. So in this example, it is decreased more than 2 times. The main factor allowing optimization here is blockage of receptors on damaged cancer cells by the first dose, which exceeds cancer binding capacity. And as I told previously, in this situation, the radioconjugates will be redirected to still viable cells, which represents an effective method for increasing treatment efficacy with the use of short-range particles. And when both crossfire and self-damage dominates, then the optimal treatment represents a compromise between 2 factors. So the two-dose case allows understanding the main methods towards optimization of multi-dose treatment, but how to find optimal schedule in the multi-dose case. I used the following reasoning for multi-dose optimization. We already know that the curative effect of treatment is provided mainly by the antibodies related to the attached to the cancer cells, by the nucleids on the antibodies attached to the cancer cells. So let's consider the last auxiliary idealized model where we neglect the damage from an anchored nucleus, and all the produced receptors immediately get bound by antibodies. So once a free receptor is produced, it is attached by antibody, and the antibodies can provide indefinite saturation of receptors. If the cancer cannot be cured in this idealized setting, then in the original model, achieving cure is highly unlikely. And analytical study of this model shows that the necessary but not sufficient condition for cancer curability in long term is this, which makes perfect sense, because at the left side we have the rate of cell damage, and on the right side we have proliferation rate. And to cure cancer, you need to damage cancer cells faster than they proliferate. And the damage rate grows with increasing radiosensitivity if the nucleus decay faster, if the cells have greater number of receptors, if the cells are located denser, and if the drug is purer. Once again, this is not a sufficient condition. The problem is that during prolonged treatment, the irradiation rate of cancer cells is inevitably mitigated by the accumulation of inert antibodies on its receptors. And the account for this effect allows driving more strict conditions, which are quite cumbersome. So I'll just illustrate them on these parametric plots, where axis corresponds to the death rate of cancer cells and their radiosensitivity, while 3 plots are obtained by variation of significance of self-damage and crossfire. The green zones correspond to the cancers that can be cured via initial saturation of cancer receptors, which is close to the cure by a single dose. Yellow zones show cancers that can be cured by prolonged treatment due to only self-damage effects. And red zones, for them, self-damage is not enough, but with additional crossfire, the cancer can be cured. And for these cancers, the ratio of viable and damaged cells tends to a stable value. And if it is low, then cancer can be cured. And the interesting trend that these plots show is that if all other parameters are equal, it is easier to cure cancer by single dose if crossfire dominates, but it is easier to cure cancer by multiple doses when self-damage dominates. Yeah, and interestingly, when crossfire dominates, then some cancers with low cell death rate can be cured by a single dose, but remain uncurable in the long term. So the response of cancer to the initial dose resembles a pendulum swing that may and may not cross a curative threshold. And the long-term drug infusion is similar to a push with a constant force that just may be not enough for cure. And this idealized model is useful not only for such qualitative understanding, but it was also used for multi-dose numerical optimization. Namely, I discretized the dose administered in this model in different ways and used thus obtained schedules as initial conditions for the multi-dose optimization in the original model. So let's return to the in silico trial, and here is the extension of the already discussed result for the single dose setting, where mice are stratified into 3 groups corresponding to low, intermediate, and high relative significance of self-damage. So red curves show the outcome of administration of one-size-fits-all maximum tolerated dose, and its efficacy does not seem to depend on the range of particles. Green curves correspond to numerical optimization of the single dose, assuming precise knowledge of all the model parameters. And the greatest increase in efficacy is achieved for the group with intermediate values of Ks, because these mice benefit both from slow decrease of crossfire irradiation rate and from redistribution of a part of radioconjugates to newborn viable cells that promotes their prolonged self-damage radiation. And these curves illustrate the results of multi-dose optimization in the that I have just talked about. So we know everything about every mice. They are close to the theoretical limit of the most ideal personalized treatment. And what can we achieve given the uncertainty of parameters? As earlier, the only parameter that I assume to be known is cancer binding capacity at the moment of the first injection. And we also can set the limit on injected doses, guaranteeing that they will not be lethally toxic in total. So these are the assumptions. And using these assumptions, I found the universal optimized schedules with doses tailored to cancer binding capacity. Within them, the first dose is about 1.4 of cancer binding capacity, and all the next doses are about 0.1 of it. And they are administered at certain intervals while it is safe to inject them. These schedules were obtained for another set of mice. So how will they perform in this set? And here are the results. This approach yields the greatest increase in efficacy for the groups where self-damage is moderate or dominates. For the latter group, it leads even to greater rate of cured mice than predicted by explicit numerical optimization with the knowledge of all parameter values. For these universal schedules, the initial dose saturates the cancer receptors to enable a redistribution of the following significantly lower and low toxic doses towards still viable cells. And this is a robust optimization method valid for the use of short-range particle emitters and high affinity or rapidly internalizing antibodies. On the contrary, if crossfire dominates, we can achieve only a moderate increase of treatment efficacy. And the optimal dose intervals will be shorter because they allow getting advantage of the relatively slow process of cancer mass shrinkage. But no matter how you optimize the treatment for this group, the result is basically the same. If crossfire dominates, then we can optimize treatment in a robust manner only by a moderate level. Now, moving to conclusions. This study is based on a highly idealized mechanistic model of the kind that is generally referred to as spherical cows or spherical horses in vacuum. However, such studies of simplistic models are very important because they allow to uncover the methods of treatment optimization that should be robust, at least in theory. And I really love this quote of Alan Turing, so let me cite it with small adjustment. Mechanistic models can be defined as simplifications, idealizations, and consequently falsifications. However, if the features retained in them are of greatest importance, then we can go a long way with these models. And yeah, as you probably know, this approach allowed him to explain how stationary patterns can emerge in nature using only just 2 simple equations. And his idea has been validated. For example, fingers do appear by this mechanism. And I believe that by gradual model improvement, in particular using quantitative systems pharmacology, we can get increasingly closer to reality, turning our spherical horse into a magnificent stallion that will predict the effects of radioimmunotherapy in patients. The major outcome of this study is the general principles for optimization of radioimmunotherapy, which generally should be valid in patients as well. The first of them is the importance of nucleate to antibody ratio. It is important since the density of radioconjugates on cancer cells determine the radiation density deposited in them. And as I mentioned, the labeling ratio in our experimental setting maximized the use of actinium-225, which is an expensive material. However, the use of higher labeling ratios should be beneficial, despite that it will result in some fractions of actinium going to waste. The second principle is cancer binding capacity-based dosing. The total number of specific receptors on cancer cells is the critical factor for treatment optimization, which estimation may allow increasing treatment efficacy close to its theoretical limit. And the third principle is particle range guided multi-dosing, since the use of short range particle emitters and high affinity or rapidly internalized antibodies can allow redirecting the dose towards still viable cells, yielding robust method of treatment optimization. And it is noteworthy that eradication of cancer cells via self-damage may be a necessary condition for optimization of treatment of blood cancers, since during prolonged treatment, the distance between remaining cells should gradually increase, hindering the efficacy of crossfire. Now, what are the problems that should accompany clinical setting? First of all, daratumumab has its own mode of action. It induces immune response. Well, I don't consider it as a problem, because if we aim to cure cancer by radiation only, and some additional effect increases the treatment efficacy, then that's great, let it be. An important moment is that daratumumab is low toxic by itself, and it can be used in large quantities saturating cancer receptors. However, prolonged saturation of CD38 receptors was witnessed in clinical setting several weeks after termination of daratumumab administration, since it is cleared from the body very slowly, and it stays there for long, which underscores the necessity of tailoring the first dose to cancer binding capacity for efficient prolonged radioimmunotherapy. If you don't do this, then it really does not matter much how you inject the following doses. In this task, I proposed a highly idealized technique for measuring cancer binding capacity. In reality, an important problem is that daratumumab initially predominantly binds to healthy immune cells, expressing CD38 that circulate in the bloodstream, as our group has previously shown. And for the clinical trial, we use a cold dose of unlabeled daratumumab to saturate healthy cells and allow redirecting radioconjugates to cancer cells. However, after healthy cells are saturated, the problem still persists. You should not oversaturate cancer cells. And I believe that in reality, we can leverage the fact that the microenvironment of cancer cells, blood cancer cells, are subject to a swift exchange of substances with the bloodstream. Therefore, during the slow, continuous infusion of drug performed by some lateral flow microfluidic chip-based device inserted in a patient vein, along with this slow continuous infusion, it can perform the estimation of the degree of saturation of blood cancer cell receptors in a dynamic way by monitoring the blood radioactivity level. And such device will seize the drug inflow when treatment shifts from beneficial to harmful. And relevant devices are being developed outside of radioimmunotherapy area. Then the saturation of cancer receptors will enable redistribution of small and low toxic subsequent doses towards still viable cells. Another problem is that cancer populations are notably heterogeneous, while this model deals with homogeneous cancer. Nevertheless, the derived principles still should apply. And the next problem is toxicity to healthy immune cells expressing CD38, which should also be accounted for. However, low levels of expressions of CD38 in healthy cells can protect them from excessive irradiation. And finally, these principles can be translated on another blood cancer setting and on antibody drug conjugates with cytotoxic payloads, which is intriguing since antibody drug conjugates can become one of the major pillars of cancer research in the upcoming decade. Thank you for your attention. I will be happy to answer more of your questions.
I think we have time for questions. Okay.